I think we're good to go. First, thank you so much for coming to this final awards session, staying awake the whole week. I'm sure you're all pretty exhausted. It's been an exciting and riveting and exhausting week for me, too. And thank you for the recognition, especially to Matt and Volker and the committee for looking at this work and recognizing it. It's quite the honor, so I really appreciate the recognition. I want to start off by trying to just recognize the broader community that just made the work possible first. And that'll be one of my first points, is just talking about community. So I'm going to start off by just giving some sincere thanks to people who really shaped some of the ideas behind the Y-line. And the first person, an attendee here, is my undergraduate research mentor, Margaret Burnett. So she was just instrumental in me being here at all. She introduced me to HCI and software engineering. She taught me how to think, how to read, how to write, how to develop scientific arguments, and this was all when I was just a freshman as an undergraduate at Oregon State in computer science. I would not be a scientist if it weren't for her. I would not be standing here today if it weren't for her. So she really helped me navigate my way to graduate school, and she deserves a lot of recognition just for all of the mentorship that she's given me and all of the other students she's mentored in the past. All right, next thank you is Brad, my advisor and co-author for this work. 10 years ago when I started publishing this, and the several years before when we started thinking about these ideas, he was the one who seeded me with this really interesting and provocative vision of what if machines had to explain themselves? That was the question that he asked me, and it wasn't really much more than that, but it was a vision to try to chew into and think through and try to understand, and it was really just his relentless constructive critique and his really unbounded availability to just help me learn, that helped me move through that problem really quickly and give me guidance on it. He was an amazing mentor as well, so I just want to thank Brad for that too, even though he's not here. Let's go ahead and give him a round of applause too. Another thank you is you. This is my 13th ICSE. I've been part of this community for quite some time, and every single year, this community's taught me all kinds of fascinating things about technical rigor and really tested the limits of my humanism that's really driven a lot of the background that I have in HCI that I've brought to software engineering. And so I really want to thank this community for really giving all of these really powerful ideas from then 30-year history of dependencies and analysis and architecture and program comprehension and encapsulation and modularity. These are things that were not part of my training in HCI, but became really part of the foundational expertise that I had that allowed me to do that. So pat yourself on the back for really making valuable ideas that were there for me to build upon. And then finally, in getting to one of the bigger ideas, is thank you to academia in entirety. When I think back on sort of all of the time that I've spent doing research and this project and other projects, I've been really fortunate to have a lot of really amazing and outstanding teachers across my lifespan. And I think a really important point is that it hasn't just been teachers in computer science in my higher education, but teachers throughout K-12 in all kinds of subjects. So I'll just list some here because I think they're really interesting. Great teachers in physics, sociology, math, psychology, neuroscience, business, English, philosophy, design, art, learning, and even chemical engineering. I took a one-credit chemical engineering class on plastics and had professors and teachers in all of those contexts that were really formative in how I think about science, how I think about research, how I think about engineering. And a lot of my ideas, and I think many probably of your ideas, are just compositions of some of those ideas that we've learned from our teachers. So I think recognizing that this is really a broad community effort that we're all engaged in and not something that we're all doing in solitary is a key part of thinking about how we do scholarship. So I want to transition now to talking about big ideas, and because of all of the community that's really shaped my ideas and the ideas that we've built upon, I want to talk a lot less about the ideas in the Y-line and a lot more about where they came from. But to do that, I want to use the Y-line as an example, use the project as an example, and so I'll give a little bit of a primer on the Y-line and its impact just so we all have some common ground to build upon. So here's the brief primer. There's me 10 years ago in Leipzig, Germany, about 900 kilometers south of here. This was at ICSE presenting the work originally. And this was actually just one of 4 papers that I published on this idea across 7 years during my PhD and my first year as faculty at the University of Washington. And I'm going to try to just distill all of that work into just one slide to give you an essence of what the core insight was that made the work actually valuable. And so here's the key insight, and I'm going to frame it as a theory. So debugging is slow because developers iteratively test really brittle hypotheses about what caused the failure by manually collecting runtime data. And this little visualization you'll see on the right, it's sort of bouncing back and forth between possible explanations, right, as you gather data. So this is sort of an abstract description of what most of you probably experience when you're debugging, right? It's a lot of guessing and checking of your belief about what happened at runtime. Eventually we get there, and that's fine, but I argued in this work that this is slow because there's not a lot of guidance around what you're certain about and what you're not. So there's just a lot of guessing that drives that process, and that revision takes a lot of time. So the argument here was that debugging would be faster if developers worked backwards from some well-understood failure that they knew was a failure, and then rigorously and systematically worked from that known failure from cause to cause, verifying the underlying reasons for why that failure happened. And this is really just saying that a root cause analysis that works backwards with evidence is going to be faster than the scientific method, which involves generating hypotheses, testing them, refining them, and until you converge towards an answer. So that's what the essence of this idea really was, right? It was about strategy. It was about talking about what would make for a successful and effective debugging strategy. And so the way that I demonstrated that that was true was really by building a tool that sort of encapsulated that big idea. And the tool was, in essence, just capturing an execution trace of everything that happened at runtime and reconstructing a history of output, and then allowing a developer to interrogate that output and say, well, why was this line black? It should have been something else. Or why was this value 6? Or why didn't this happen? And by starting from that known failure, which is really strong evidence, and working backwards, you can get to the cause. And so then the way that we responded with those questions that developers selected in the interface is by giving them an answer, which was a precise backwards dynamic slice on that output property that they selected. Now, the really key thing here was that we did not give them the entire slice. If you don't know program slicing, the idea of a slice is to give the subset of things that happened at runtime, for at least a dynamic one, that ultimately contributed directly or indirectly to causing that value at runtime. But instead of giving all of those lines of code and all of those runtime events that happened, we just gave an interactive slice and let the developers step one step at a time through that causality, verifying the things that they observed, and using all of their knowledge of the architecture of the system and its requirements to try to understand what the source of the defect actually was. And that was a really key insight, that it was their knowledge that was actually making them search through that slice more efficiently and effectively than before. And I'll get back to this later when I make a point. So just to summarize some of the key results here, novices with the Y-line debugged 8 times faster than novices without it in one study. Novices with the Y-line were about twice as fast as experts without the Y-line. And experts with the Y-line are about 3 times more successful and twice as fast than experts without it. So these are pretty big effects, really coming from that core observation that root cause analysis is better than the scientific method when it comes to debugging. I won't dwell too much on impact. That's not why we're here. I want to make this a valuable talk for you, but there were lots of papers that cited it, lots of techniques that built upon it across lots of different fields of computer science, and it triggered a lot of resurgence in sort of looking at dynamic and time travel debugging techniques, and so I think those are really exciting and powerful things. There was also some industry impact and continues to be. It triggered Adobe to start thinking about debugging tools in this way, Microsoft to start building lots of time travel debugging tools in this way, and continues to now for other platforms like JavaScript. And then some of my students have gone off to other places to take some of these ideas as well. So Apple and Safari's developer tools are looking at this with my student Brian Berg, and Code.org has just started adopting these in some of their educational technologies for teaching computer science. Now, all these ideas, all this evidence, all of this impact is great, but how much credit do I really deserve, right? If you look at some of these ideas, it's, again, just a composition of a lot of other ideas from other places. And in fact, a lot of the process that I used to arrive at them was following practices from really old ideas about how to do scholarship that are important to think about too. So I want to talk about some of those big ideas from science and just show how it is that Brad and I arrived at these ideas, and how it is that you might leverage some of those same old ideas from science to try to improve your work too. So here's big idea number one. Reading accelerates innovation. So Linus Pauling, who was also an Oregon State alum like myself, he was a Nobel laureate in chemistry. He said the way to get good ideas is to get lots of ideas and throw the bad ones away. And there were a lot of places where this was posted on campus, and I saw this a lot while I was walking around Oregon State. And so when I saw this as an undergraduate, one of the ways that I interpreted this was to never forget that there are really hundreds of thousands of research papers in the archive, all with really powerful ideas, and that we should use them. We should leverage them to inform our work, right? We should just read them. And so one of the things that I did when I was first starting in graduate school and beginning work on the Y-line was spent 3 months reading all of the papers I could find, not only about debugging, but about every other related topic, whether it was diagnostics, human error, root cause analysis, anything I could find beyond the boundaries of CS and within the boundaries of CS that might be relevant. So when I was doing this work, it wasn't that I was so creative that I came up with this idea of thinking about diagnostics in a different way. It's that I was leveraging ideas that had been built off of 100 years of research from other disciplines, not just my own. Here's one of the papers that was really impactful. You might not know it existed, but Mark Weiser's original program slicing paper cited it as motivation for that original algorithm. And it was actually a paper published in a human factors journal by a psychologist who happened to be studying debugging. And it showed that debugging required analyzing data flow, that developers satisfied their data flow analysis. They didn't do it completely, they kind of did it partially, and that they analyzed many more irrelevant statements than relevant statements because they had no guiding theory about what the cause of something was while they were debugging. That was the basis of the work that I did. So it was this paper from 26 years before I had started this work that was really the inspiration for some of these ideas. It wasn't that I had just come up with this idea out of nothing. I really borrowed it from something that had been around for a few decades at that point. All right, big idea number two is that observation develops insight. And I think this is a subtle point, but Alexis Carrel, another Nobel laureate from physiology and medicine, he said that a few observations and much reasoning lead to error. Many observations and a little reasoning lead to truth. And the idea here was similar to the training I received in HCI, which was I took this to mean that if I didn't deeply understand the phenomena that I was trying to investigate, which was debugging, I couldn't simplify it. I couldn't fix it. I couldn't change it. No matter how much I reasoned about it analytically, if I didn't have an intuition for how debugging worked, I wouldn't be able to sort of understand what was going to work when I was inventing new technologies. And so before ever laying down any code or writing any prototypes, I spent another 3 months reading and observing people debug. Hundreds of novices and experts, and reflecting on my own debugging practices. And this led to this really rich intuition around how debugging works as an activity, not just one that's grounded in data and evidence and analysis, but one that was just grounded in observation, right? It gave me an intuition. And I still use this intuition today when I am doing my own research, when I'm reviewing papers about debugging. These are the kinds of intuitions that I use to judge, is work moving in the right direction? Is it going to solve a problem? So we really can't discount this intuition in shaping the more objective work that we do in science and engineering. All right, big idea number 3 from science, explain why, not just how. I'm going to go all the way back to Leonardo da Vinci, who said, "He who loves practice without theory is like the sailor who boards ship without a rudder and a compass and never knows where he may cast." So I took this to mean that the true value of inventions, including the technologies that we all make here, is that it's not so much in what they do and how they work, but why they work. Why would it be that any of the things that we invent actually are effective in practice? That's theory, right? That's an explanation for why something works. And it's these explanations that are actually the generalizable knowledge that stands the test of time, right? It's what allows that knowledge to transfer from tool to tool. My Java Y-line prototype that I published, right, and did experiments on doesn't compile anymore. Nobody can actually use it, right? The thing that lasts is actually the explanation of why it worked. And that's the thing that transfers to whatever new version of that somebody might create in the future. And so the key thing that made the Y-line work was that intuition about debugging and a theory about what would make it effective. And it was that theory and not the tool itself that was the core of the innovation. So one way that I like to think of tools that we invent is actually as embodiments of those theories. They're a way of manifesting our beliefs about how people do their work and what's going to shape their work. And tools are something that can guide that and mediate that, but they're sort of secondary to that big idea underlying it. All right. All of that is to say that most of the ideas in the Y-line I borrowed from other places and assembled together, and that's how creativity works, that's how innovation works, that's how science works. And so none of these practices and none of these ideas were really my own in isolation. But when we do research and we compose them together and we find new things from that, there are new things that we discover. I didn't really know what was new about the Y-line when I did it. I felt like this is a nice tool, and it seemed new, and other people thought it seemed new. 10 years later, I understand a bit more about what is new about it and what's significant about it. So I'm going to share two ideas that have shaped my work over time, but have also been influenced by lots and lots of other research in software engineering, in HCI, and other fields. And I think these two big ideas are something that are relevant to most of the research that we do in this field, so hopefully these are valuable to you as you move forward. Okay, big idea number 4. Automation is insufficient. So Mark Weiser in the program slicing paper, this is what he said. He said, in practice, slicing is fairly fast, here's claim number 1, and can often eliminate large numbers of unnecessary statements from slices of programs. That's the only claim he ever made in that paper. He never said it was useful in practice. Right? He said, this is an algorithm. This is what it can produce. This is its output. He didn't say, this is going to make people a lot faster at debugging. He didn't make any of those claims. And in fact, if you look at the 4,500 papers that have cited this paper, only 3 of them actually evaluated whether or not slicing was useful. And all of them found that slices are always too large, they're always too hard to navigate, and they're almost always incomprehensible at scale, and people can't do anything with them. They're not actually valuable or useful. Right? So that simple algorithm, which is really powerful and led to a lot of research in our community, just wasn't sufficient to be useful. Right? That's a really important observation for us to make. And the field's key mistake in all of that work was just assuming that useful slices are trivial for developers to express. It turns out when I investigated this with the Y-line, people didn't know what thing to investigate, what variable to investigate. And so we had to have an interface in which somebody expressed things about output, which they did understand and could interrogate, but they couldn't choose which variable to do a slice on. That wasn't something they could do well. And then second, the size of a slice actually doesn't determine its comprehensibility. Right? That was the belief in those 4,500 papers, that we need to make these things smaller, because if they're not smaller, people won't understand them. But the Y-line showed that that wasn't true. Right? So we needed a sort of investigation of utility here to understand that expressing a slice is hard, and there needs to be an interface for it, and that navigating a slice is hard, and that doing it interactively is actually more effective. And this actually required an entire re-architecting of how I did slicing on the Y-line, because it just didn't make sense as a batch algorithm. It only made sense as an interactive one. And so when we look at this in other settings, a lot of other people in this field have shown that automation is insufficient too. On refactoring, on static analysis, on machine learning, in most of these cases, also in HCI, you can throw a batch algorithm at someone, they won't understand its output, and suddenly you have to reconsider how to redesign it. And that's where a lot of things are moving in other fields. It's thinking about what happens when you take something interactive and you put it in an interactive loop. And so this is probably also true for a lot of the things that we work on in formal verification, program synthesis, testing, bug patching. What does it mean when there's a developer in the loop? And this leads to my last idea, which is that human augmentation, in most cases, in all of the evidence we've seen so far, is often more powerful than pure automation. We like to believe that with enough data and the right algorithms, our tools can really outperform all of the developers we're trying to help, and that we will someday replace them. I hear this a lot from my friends, especially in AI. And the Y-line showed that this just overlooks the power of developers' knowledge, of the things that they know about source, and the things that they even know about source they've never seen. So in the evaluations of the Y-line and the studies I mentioned, participants interacted with slices that would have been about 50,000 lines of code or larger, which should have been incomprehensible, right? But they actually only looked at about 30 lines of code when they were actually doing this. It just didn't matter how large they were, because they knew a lot more about how the system was architected and only had to look at 20 or 30 parts of that causal chain to identify where the defect was. So we ignore all of the knowledge developers have at our peril, and by leveraging the knowledge that they have, we can actually create systems that are much more powerful than we might expect by combining the expertise that a developer has with the ability for systems and tools to be systematic and thorough. And so there's a couple of consequences here if we ignore what developers know. Our innovations either aren't useful because they don't account for what developers know and they sort of collide with what developers know, or we just miss an opportunity to combine human and machine insights for even greater power. And so that's sort of a challenge to you, is to think about how to invent your tools for software engineering that focus on the entire system of your tool plus a developer, or your tool plus a developer plus a team, or your tool plus a developer plus a team plus an organization. And if you do that, not only will your tool have more impact, but it'll actually be more powerful than just the tool alone or just the developer alone. So that's the wisdom, and I'll just restate these just so you have them in your head. Read everything in and outside of CS and build upon it. That's so critical. We just don't do that enough in this field. We just don't read enough. 2, reasoning about a problem is insufficient. Go get a really personal, rich instinct about the problem that you're trying to solve by observing it. 3, try to explain why your tools work, not just how they work. Figure out why it would be that they would be so powerful. 4, don't assume that automation is enough. Developers know a lot more than you think, and they probably can do better than your tool. Figure out how your tool can make them smarter. And then 5, try to invent ways that combine all of that developer knowledge with machine insight. I think there's real research discoveries to make in that class of architectures that we don't investigate often enough. Thanks for your time and attention, and I'd be happy to take a few questions.
If you have questions, you can either come to the mic here or a mic back there. We have a couple minutes for questions. I'm sure Margaret has a question. She does?
Got a question up here.
I'm sorry, I can't see. There.
Waving hand.
So I heard through the grapevine that there was a version of Y-line for Microsoft Word. Is that right?
Yes, there was a paper that Brad and I did with an undergraduate where we applied similar ideas to just a word processing interface. And the interesting thing there was that since the user of that word processor was not looking at the source code of the word processor, they were just dealing with its input and its output, we were trying to find out if similar ideas would work in that space too. And the interesting thing there was, what's an answer if not the internal causality of the software that's causing a word processor to do something? So here's an example. Your autocorrects a word, and you don't know why it did that, and you don't want it to do it anymore. So the idea was you just point on that word and say, why'd you do that? And then the answer that it gives is all in terms of the underlying user-visible inputs that caused that to happen. And in a word processor, that's often the checkbox that had that mode set on, right? And so you immediately go to that checkbox, and that's your answer, and then you can turn it off. So a really similar idea, kind of a different manifestation from an interface perspective, but the same sort of underlying algorithm. We just built it architecturally using an undo stack instead of precise backwards dynamic slicing.
I'm over here.
Oh, okay, right there.
Hey, hi Andy, what do you think is the role of tools in this community? It seems like there's a variety of different work. Y-line is an example of a fantastic tool. Lots of people are building tools. Conceptually, what do you think is a kind of a tool? What's the role of a tool in a research paper?
Yeah, that's a great question. So I spent some time in industry and have a good sense of what tools mean in industry. And in industry, tools are really powerful things that shape your process and your work and accelerate what you're doing, give you information and knowledge. And we like to think of them that way in research too. But in research, I tend to think of them as something a little bit different, right? Because the output of our work in research is a PDF, right? It's not an implementation. Maybe it's also an implementation that we share with the world, but in that case, what we're really doing is producing tools. So I think we also have to think when we write that PDF, what is the robust, lasting knowledge in that PDF that's powerful? And it's not a tool, right? It's an underlying idea about what shapes work to make it more productive, what makes a developer think more effectively. And those are those theories of our tools that we don't often make explicit. So James Herbstop and I were talking about what would it mean if all of us tried to really explicitly state in every paper we write when we contribute a tool why we think it's going to be effective in just one paragraph. Right now, when we read most papers, it's sort of 2 or 3 words or maybe a sentence, and it's sort of implicit. Let's make it explicit and interrogate whether or not those reasons are reasonable.
As a second question, if knowing everything that you know now, if you could go back and change something about that work that you've done, what would that be?
Part of it is actually sort of the impact of it from a tech transfer perspective. So it turns out that when you re-implement the entire runtime stack in order to create a debugging tool, getting that to transfer into product is really, really hard because you've changed so much about the way things work. And so I think there are versions of that prototype that would have been a little more reduced and a little more sort of the essence of the idea that would have been easier to put into the world and get into products. So a lot of the impact that I mentioned, it was getting little pieces of that architecture out into the world, but not the entire thing. So when you think about your ideas, try to think about how to reduce them to their essence so that you can find a way to get them into the world more easily, because every extra line of code in that prototype is probably an extra 6 months of implementation effort when you're talking about a real product.
Okay, I'd just like to thank Andy for both the Y-line work and the reflection on the Y-line work. And I think my students probably are not going to thank him because I'm going to suggest they go read 900 papers. So let's thank Andy.